So the last thing we talked about, I'll add a page because we're going to talk about the transition state and all that stuff. So the last thing we talked about is just the mechanism, like how the reaction happens and how the diene and the dienophile react together to give you a 6-member ring, how it's stereospecific. And now we want to talk about another aspect of the reaction that deals with the molecular orbital aspect of this reaction. So we're going to talk about right, and we'll use the transition state to discuss it. Right, so the way this works is your diene is here. And you should have seen this in the video that I sent out. All right, this is your diene. It's a 4-pi system, so you got 4p orbitals. And this is your dienophile, which has 2p orbitals. Now, in order for this to overlap, and in order for the orbitals to interact, these orbitals here must have the same sign, right? So you gotta have the same sign. Remember we talked about a p orbital having a node in the middle. Right, and then one lobe is, we'll say we're going to shade it. One lobe will be shaded, and the other lobe unshaded. Right, so the orbital itself is made up of these 2 lobes, and they have different signs. Right, either positive or negative. Let's think about it that way. Because it's with the orbital itself just being an equation, a graph of the equation of the path of electrons, it can, if it's an equation, it can have a positive sign or a negative sign. So when we think about that in terms of the transition state for the 4+2, right, we have to think about it in terms of molecular orbitals. So we said that this is a 4-pi system. So the molecular orbitals look like this. We got 4 molecular orbitals that are capable of reacting right, and we talked about this already, right? These 4 molecular orbitals, they have wave and particle-like properties, right? So wave-wise, this is going to be the first harmonic, so the wave will never pass through 0. And then here, the wave passes through once. Right here. So you have a node there. No nodes in the first harmonic. And then when you get to the top, it passes through twice. Like so. So you got 2 nodes. So that's shaded. Then the sign changes and it goes back. Right? And then here, the wave is going to pass through 3 times. 3 nodes and 3 sign changes. All So with that, that's my 4-pi system. And remember that 4-pi also indicates that there are 4-pi electrons, right? So the way we put the electrons into the molecular orbitals, just like you would do an atomic orbital. You follow Hund's rule, and you fill up the low levels first before you touch the upper levels, right? So I'm going to put 2 electrons here and 2 here, right? This, where the 2 electrons are here, we call that the Homo. It's the highest occupied molecular orbital. Right? And then right above it, the empty orbital above it is the Lumo, what we call the Lumo. And that is the lowest unoccupied molecular orbital. So that's one of the key concepts with molecular orbital theory is Homo and Lumo, right? The Homo is if the diene is acting as a nucleophile, it's going to react through its Homo. Right? And what that means is that that's the molecular orbital responsible for its reactivity. And if that's the case, then whatever that molecular orbital is reacting with, somehow the signs of the orbitals have to match up. And I'm going to show you that in that transition state. So if it's nucleophilic, let me fix that up. It looks sloppy. Right? It'll react through the Homo. All right, so only if it's acting as a nucleophile, it's going to react through the Homo. And then with the Lumo, the lowest unoccupied molecular orbital, right? That's an empty orbital that can accept electrons. So if it's acting as an electrophile, then that's where it's going to react. That's the orbital that it'll use to react, is the Lumo. Right, so if it's nucleophilic, it's going to react through the Homo, because that's where the electrons are. And they are high energy electrons, so they're more accessible. If it's electrophilic, then it's going to react through the Lumo. All right. Now let's think about that 2-pi system. So our word got cut off. All right, let's think about the 2-pi system. If it's a 2-pi system, how many pi electrons are there? We got 2 pi electrons. How many molecular orbitals? If you got 2p orbitals, that's just, so for 2 pi, that's just like a regular alkene. It's a simple alkene. How many p orbitals would you have there?
One.
Wait, okay. You got 1 on each carbon.
So 4 or 8?
No, not in this case. Look at the double bond. You got a p orbital on each carbon, right? If it's a 2 pi system, then that means you have 2 p orbitals. Right? If it's a 4 pi system, you got 4 p orbitals. If it's a 6 pi system, you got 6 p orbitals.
So when it's saying 2 pi, it's just 1 pi bond.
Yes, but you got 2p electrons, right? 2 pi electrons, because one electron in each one of those p orbitals that make up the pi bond. So that's why we call it a 2 pi system.
Okay.
That's a good question. All right. So with that, if it's 2 p orbitals, atomic p orbitals, then you're going to have 2 ways that those orbitals can combine into molecular orbitals, right? So it follows the same principle of a standing wave. So here, both of these are going to be the same sign because the wave never passes through 0. And then here, the wave passes through once. My P's look beautiful. So the wave passes through once. So this sign is going to change. All right, then we put the electrons in because it's a 2 pi electron system. We're going to put them here. So for a 2 pi system, this is the Homo. And then this is the Lumo. Keep in mind, the O in Homo is occupied, meaning that it contains electrons, and the U in Lumo is unoccupied. So that means it's an empty orbital. All right. So how do we apply this to the transition state of the Diels-Alder reaction? Well, in the transition state, it's always the Homo of the diene reacting with the Lumo of the dienophile, right? So what does that transition state look like? Well, you got to know what the molecular orbital looks like for the Homo. So let's go back to here. If this is the Homo, right, we're going to shade these orbitals like they are in the Homo. So this is going to be shaded. This is shaded. And then over here, the sign changes because of that one node, so that's shaded. Are y'all following? Anybody not see that?
Why
Right.
does it change?
Go ahead.
Why did you say it changed?
Well,
Tom?
based on the molecular orbital diagram that we have over here.
Oh, okay. I see
Right.
it.
You see where in the second harmonic, the wave passes through 0 one time. And so that's going to cause the signs of your orbitals to change.
Okay.
Mm-hmm. So how should I shade? And let me get this out of the way.
I have a quick question.
Go ahead.
So, well, if you are you able to like zoom back out to
Yeah.
the some more. Okay, so the purple.
Mm-hmm.
How are we determining the line, like the way the lines are going?
You mean the wave that's passing through?
Yeah, the waves. Like, how are we determining?
It's got, okay, so that's a great question. So with the wave, when the wave passes through and makes a node, like here, right, when the wave passed through 0, right there, it's got to be symmetrical. So anytime that wave passes through, it's got to cut symmetrically. It cannot fall on, well, it can fall on top of an orbital, but not in a 4 pi system. In odd number pi systems, that's when you see the wave, it might land on top of an orbital, and that orbital is non-reactive. But for 4 pi or even number systems, the wave has to be symmetrical. So it's got to cut symmetrically. So that's how I know to put it right there between the two. And then up top, you see in the third harmonic right here, right where I have a node right here and a node right here, that's because it's got to be symmetrical. Like I can't cut it and have my 2 nodes. Let's say, for instance, if I put, I'm trying to do this without making it crazy looking, but let's say, for instance, I put a node here and not here, right? So that's what my two nodes would be. That's not symmetrical. You following that? So it's got to be symmetrical when it cuts or when it passes through. So that's
Okay.
how I know where to put it.
What about the first wave?
Well,
If
that wave never passes through zero. That's why all the orbitals have the same sign.
Oh, okay. Okay.
Right? See how everything is shaded? The top lobe with every one of those p orbitals is shaded.
Mm-hmm.
Yeah. So that means that the sign is not going to change.
Okay.
Mhm. Good question. All right. So we're going back up to here. Now, this is the HOMO of the diene. We already confirmed that by looking back at the molecular orbital diagram. How should that Lumo, how should it be shaded? Which lobe should be shaded and the orbital on the right, on this side?
The bottom one. I mean, the top one.
Okay. So you wanna shade this one. Is that right? Yeah. And you're right. This has these orbitals again, they gotta have the same sign. In order for them to overlap properly, those two have to be shaded. Or if the other one was unshaded, then they both have to be unshaded. This is what you call constructive overlap. Right? That's what we call constructive overlap. When the orbitals have the same sign, they can overlap and they add together. It's just like if I were to add two equations together, they were both positive, then they're going to add together and increase in value. Right? If one was positive and one was negative, and they had the same value, they cancel each other out. So that's what this is. Right? So in order for orbitals to properly overlap, they have to have the same sign. Right? And if on the other side, how should that on the left side, what should that look like?
The bottom one shaded.
Yeah. And we can go back again, we'll go back to the Lumo and we can see that, right? The Lumo of the 2-pi system, do you see it? I mean, that's what it looks like. We can turn it around so that the orbitals match, but one of those orbitals has the top lobe shaded and the other one has the bottom lobe shaded, right? Because the wave passes through zero and it causes a sign change. Right. So when the transition state happens, it's the HOMO of the diene and the LUMO of the dienophile, and your orbitals must match. If they don't match, then instead of constructive overlap, you're going to get destructive overlap. And I'm going to put that down here somewhere.
What do you mean when you say like the Lumo is like empty, like unoccupied?
No electrons. You see how when you compare the two orbitals, you see how you got 2 electrons down here?
Oh, okay. How come the picture's the same?
Hmm?
Like you would still draw the orbitals if there's no like electrons.
Yeah, no, the orbital still exists because even if it's empty, it can accept electrons.
Okay.
If it can't take electrons, I mean, if it can't donate electrons, it can still accept electrons. So it still exists. It's just empty. It's like if you leave your apartment to go to class, your apartment doesn't disappear, does it?
No.
Yeah, it's still there when you get back, but it's just unoccupied when you leave, right? So it's the same idea. The orbital exists based on the fact that you got 2 p orbitals, 2 atomic p orbitals that can combine to make 2 molecular orbitals. And just because it's empty, that doesn't mean it's non-existent. It's just there to accept electrons, right? Empty orbitals accept electrons, full orbitals donate electrons. Does that make sense?
Yes, it did. Thank you.
Okay, all right. So down here, let me just talk about the overlap. Let's see. So you have if you have two orbitals that are overlapping. Now I'll draw it like this. And this is shaded, and then this is shaded. When they overlap, right, they're going to cancel each other out. This is what you call destructive overlap. Right? And then if you have orbitals that have the proper sign, like so, like this is shaded and that's shaded, then that's good. This is constructive. If I can fit that in there. Nope. Top. Right, so that's when you're talking about orbital overlap, it can be either constructive or destructive, but you want it to be constructive. All right, any other questions about that, about the transition state for the Diels-Alder and the Homo-Lumo interaction? So again, so let me ask this question. If the Homo of the dienophile is reacting with the Lumo of the diene, which one is acting as the nucleophile?
The Homo.
The Homo is the nucleophile. It's giving away electrons, and then the Lumo, because it's empty, is accepting electrons. So the Homo is acting as the nucleophile. Great, that's a very observant answer. And then the Lumo is the electrophile. Is everybody okay with that? Any questions about it? All right.
I have a question really quick.
Go ahead.
So the first one and the last one are neither Homo or Lumo.
No, because it's the terminology, right? The H in Homo means the highest, and I'm glad you asked that question because I didn't make this plain as I could. So energy is going up in this direction, right? So I can squeeze that in there. Right, so that's increasing energy in that direction. So you see the one on the very bottom in the first harmonic, right? That's lower in energy than the one above it. So that's what the H in Homo means. Highest, when I say highest occupied, what I mean is the highest in energy. Are you following?
Yes, sir.
And then the next orbital above it is the lowest unoccupied. You got two unoccupied orbitals, but the one that's lowest in energy is the one above the Homo. And that's important because when you're talking about doing a reaction, like the higher the energy is of the orbital, the less accessible it is. So the Lumo is going to be more reactive than the orbital that's above it, that's empty, because the Lumo is lower in energy than the one above it. If that makes sense.
Okay, it makes sense. Thank you.
Yeah. Good question. Yeah, and I apologize for not making that plain about the energy, but everything with these molecular orbitals is based on their energetics, like where they are in terms of how close in energy they are to whatever they're reacting with. So the Homo and the Lumo, you want those to be as close in energy as possible so that you can get good overlap. 1 second. All right, any other questions about anything? And so let's go back. So this is the transition state. This is what it looks like. This is why it's stereo specific, because the Homo is going to come in from above, either above or below the LUMO of the dienophile. And so that's why whatever substituents you have on your dienophile, they have to have the same stereochemistry in the product, right? We talked about that on Wednesday. So let's go to some examples. And from these examples, I'll point out a couple of other, pieces to this reaction, as far as like the things that speed it up or things that increase the rate, substituents you can put on the diene to increase the rate, or the dienophile. So we're going to talk about that. So let's do the first reaction here. Let's run through that real quick. And we're just predicting the products, right? It helps to put the arrows in on the left side of the reaction arrow, just so you can see what's going on. But let's go ahead and number this. Right? So where am I going to start? Keep in mind, it's the diene that's acting as the nucleophile. So your electrons are going to start flowing from there. So
would you start where that for number one, that double is gonna move down to, it's gonna move down. So it's gonna be in the,
you want to move it here?
yeah,
Okay, all right, we can do that. And then that's going to force this here, right?
yeah.
And then it's
And then
going to force
that force from 6 is gonna go back to 1. Yeah.
like that.
Mm-hmm.
Great. So we're going to get again, a 4+2 cycloaddition. The core structure that you're going to make is a cyclic alkene, right? Let me fix that up. Right, there are no substituents, so this is what you're going to get, and we'll put the numbers back in. That's 1, 2, 3, 4, and that's 5, and that's 6. All right, everybody okay with that?
Yes.
Let's do the next one. All right, we have a substituted diene, and it's substituted with the methoxy group, and this is good. So this is what we would call a donor, right? Let me make it even plainer. It's an electron donor, right? So anytime you put a donor on your diene, it's going to speed up the reaction, right? Because the donor is going to make the diene even more electron rich. Right, so donors will make the diene more electron rich, and they're going to speed up the reaction. By the same token, you have a halogen on your dienophile, which is an acceptor, right? Because halogens are typically high electronegativity atoms, so they pull electron density through induction. They cause induction. So when you add an electron withdrawing group, we call this an acceptor. And we can also call it an electron withdrawing group. That's going to also increase the rate because it makes the dienophile more reactive. And I know there's a section in one of the videos that I sent out that talks about the reactivity of your dienophile. So if you add any type of acceptor, you can put a halogen, you can put a carbonyl, you can put a nitrile. There are lots of different acceptor type groups that you can add. And I'll write them, got plenty of space over here. So let's write the product in first, and I'll give you some examples of donors and acceptors. So what do you think? You want to number it? Does that help?
Could we
Yeah.
rotate it or no?
Say that again.
That the dienophile, are we able to like rotate it if it looked to make it? I don't
You
know what
need
I'm
to try
trying.
to like to line it up.
Yeah, with that, could I do that?
Yeah, you can do that.
Okay,
Yeah.
I'm not sure if that's necessary for this one though.
No, not,
Never-
it's not necessary. I know what you're saying though, because there's another problem right here.
Yeah, yeah.
We're gonna talk about it when we get to that. That's a great
Okay.
question. Great question. All right, so what's my product gonna look like? And where my arrows gonna go? Are the arrows gonna be different because it's a different problem?
No.
No, same mechanism, right? We're gonna push electrons here, here, and here. So we're gonna get a 6-membered ring. The numbers are still intact. 1, 2, 3, 4, 5, and 6. And then of course on 6, we have a bromine. And then on 2, we have a methoxy group. I'm gonna have to move that over some.
So what happened to the double bond that was with 5 and 6?
Between 5 and we used it. We used it to make this bond right here. You see how the arrow is coming from there to there?
Mm-hmm.
So that
Oh,
pi
okay.
bond is going to be used. Those electrons are being used to make the sigma bond between 6 and 1.
Okay, and then the other one is between 5 and 4.
Yep, right here.
Okay.
And then I'm moving this here. Right, so you can see all of that over here, right? This is 1 and 6. This is 4 and 5, and then this is the new pi bond right here. All right. So again, with these donors and acceptors, donors on the dienophile make it more reactive, right? And so let me give you some examples of what a donor would be. A donor would be like alkoxy group, right? Oxygen directly attached to the dienophile. It can be amine. It can be a methyl group, right? They are donors. They are inductive donors, not resonance donors, right? But anything that can donate electrons into the diene is anything like that is going to speed that reaction up. And then acceptors, which is this is a good place for this, because when we start talking about aromatics, this actually, you're going to see the same concept with reactions of aromatics. Same identical concept. So you could put something like a nitro group, carbonyl, halogens, right? And these are all considered acceptors. One of the more reactive ones is like if you use like an anhydride. Right, so if your dienophile is attached to like an anhydride or something like that, and that's a really powerful acceptor. All right, questions about that part? All right, so let's look at the third example. We're just gonna walk them down. Can anybody want to annotate this and put the arrows in? I'll go ahead and number it. If the numbering helps you, do it. It's not elementary or rudimentary. Do what you have to do to make it plain for yourself. So don't feel bad if you numbering it. If you put numbers on the test, that's just going to tell me that you know what you're doing. So don't worry about that part. All right. Anybody want to take a stab at it?
I can.
Go ahead.
Okay.
Are you able to annotate, or do I need to turn on the share function?
Mm.
Okay, perfect. Yeah, you can annotate. All right. Boom, great. So we're gonna get a 6-member ring from that. Go ahead. You want to draw the product too?
Yeah, sure.
All right. Yeah, I think I moved it. Sorry.
It's okay.
Let me go back. I'm trying to fix it. There we go. That's close enough.
Okay. Hold on. So it goes like, oops. Oh, that looks kind of janky.
That's
Sorry.
okay. We'll take it.
And then that CL is right here.
Excellent. I agree with that 100%. Yes, so you're going from here to here, here, and then like so. Excellent. And the only reason I'm writing this in is because you got it, when you erase yours, I want to have it in there, but that's 100% correct. All right. Thank you for doing that.
No problem.
What about the last problem right here? Let me put the arrows in and you tell me what we're gonna get. Right, it doesn't matter that the dienophile is in a ring. Right, you can get bicyclic products, like you get a lot of bicyclic products, so it doesn't matter.
I have a quick question. Is there a time where like the positions are switched? So like the dienophile would be
On the
on
other side?
side? Yeah,
Oh, yeah. That's
Okay.
all, yeah, that's all symmetrical.
got it.
So it doesn't matter how we arrange them. This is just just getting reps about putting the arrows in, but yeah, they can be anywhere. That's a problem that we're gonna do, I think, that has a diene on both sides of a dienophile on both sides, like 2 alkenes. So yeah, it can be on the left or on the right, it doesn't matter. Great question, by the way. So what is this product gonna look like? This part doesn't change, does it?
No, wouldn't it just be two
The
cyclic
two
structure?
rings together like that?
Mm-hmm.
Yes, that's exactly right. All right. So the ring that's in blue, it didn't change. Just because it contained the dienophile, it didn't change anything. All right. So let's look at let's go to the next example. And I want to show you something about this. Oh, can you clear off the screen? All right, thank you. So I want to show you something in the next example with this 2,4-hexadiene, right? 2,4-hexadiene is a really interesting compound because this is going to give me a chance to talk about another aspect of the reaction, which is the conformation of my diene. So the diene must be what we call S-cis, okay? So if you have a diene that looks like this, versus that, right? It actually costs some energy for that, for this alkene here to line itself up with the other alkene. So there's some rotation around this bond that has to happen, right? That's why you have to run this reaction at high temperatures, because you need the energy available for the reaction to take place, but you also need some energy available to convert the diene from what we call S-trans, which is this, to S-cis. right? So in order for that diene to react, it's got to be S cis. Otherwise, when you get to the transition state, if it's S trans, then your orbitals are not going to line up. So if this is my diene, and this is my dienophile, I can get orbital overlap here, but not here, right? Because this lobe right here is too far away to overlap with this one. Right, it might not look like a big deal on paper, but when you're talking about working, at distances of nanometers, 2 or 3 nanometers can make a huge difference, right? When you're talking about bond lengths and optimal distances between orbitals to overlap, 2, 3, 5, 10 nanometers makes a huge difference as far as like being able to actually interact and share electrons, right? So this is why S cis is necessary. So the S cis conformation is necessary for your diene. All right. So when we look back over here, we need to put that diene in the right conformation. All right. So what we'll have to do is rotate around the sigma bond here to get both dienes in what we call a S cis conformation. So the way to do that, I'll show you. It'll look like that, right? If we flip it clockwise, let me draw that. This would be if we flip it clockwise. And then we rotate around this bond right here. That's going to give us this. I'm going to move that. Now I'll move this up. All right, so that's the conformation. So it'll be that plus this aldehyde right here. All right, so I need to, I'll put it down here. Plus this. Again, you got an aldehyde conjugated with your dienophile. So that's going to be a really fast reaction. And you have methyl groups on your diene, which are also going to increase its reactivity. So same arrows here, here, and here like so. So that's going to give me a 6-member product, right? Any questions about that particular reaction? And again, the reason why I drew it initially how I did was to get, an opportunity to talk about the diene and its conformation, right? It's got to be S cis. If it's S trans and it can't go S cis, then it's not going to react, because you got to have that orbital overlap in your transition state. All right. Any questions about anything we talked about so far? All right. So we're going to continue to walk these down. I think we'll have time on Wednesday. We'll probably finish this, to be honest with you. And we'll work through some of these other examples down here, a little bit more challenging examples. But this is just to get reps and to get an understanding of how to push the electrons and the different aspects of the reaction, right? Whether it's stereo specific, whether it's the diene has to be in a specific conformation, whether, you know, and we're going to also talk about one other aspect of this, which is the endo-exo aspect that happens when you react dienes or dienophiles that contain carbonyls, and you have bicyclic systems. But we'll talk about that on Wednesday. All right. And I don't know if I'll send it today. I can't remember if I sent out the endo-exo video, but that's okay. I'll send it when I send the announcement for today.